Hey guys, thanks for tuning in again to another instructional video. This one in the topic of kinetics, especially with regards to um, integrated rate laws and how they are interpreted graphically. One example, I started with smiley the other day, so I better even it out with a frowny here. So I have some species, molar concentration, actually grams works as well, or even pressure of a gas, and it decreases over time in the usual curving fashion. Although this, that's versus time on the x-axis, but you never really know from this first initial curve if it's first order or second order. I say attempting to linearize the data, we could do at least one of two things, but the two that we'll look at, take the natural logarithm ln of the concentration. So I take these y-axis data points, this y-axis data point, that y-axis data point, this y-axis number, and take the natural log of all of those, and then replot on the y-axis. Again, on the x-axis we have time. That's almost always the case as time goes along. And on the y-axis, like I said, I put the natural logarithm of the concentration. And lo and behold, it linearizes it. Or not, but if it does, then we say it's first order in that concentration of frowny. Shrink that down a little bit so you can see the whole thing at once for a moment. Now, of course, there's a chance that the natural logarithm does not linearize it, and if it doesn't linearize it, then we're not first order in the reactant concentration. Oh, and the form of the slope-intercept form of a straight line, y equals mx plus b. Here's the y. There's the y. At some particular time equals m. The m is the slope of the line. X is the x-axis. And plus b. b is the y-intercept right there. I think that's interesting how it works mathematically like that. And if this one doesn't work, then we try the reciprocal of the frowny face, or whatever species concentration we're talking about. So again, on the x-axis I have time. On the y-axis I took the original data, and that original data was right here. Y-axis original values. Take the reciprocal of those and see if it linearizes the data. And if it does, it looks something like this. Let's see, y equals mx plus b. Here's the y, here's the m, here's the x, that's the time, plus b. B is the intercept of where the reciprocal of the original concentration hits the y-axis. I said if this linearization is successful, the reaction is second order in frowny, and there's our integrated second order rate equation that we saw one video ago, I think it was. There are very rare cases, very rare, where a reactant is zero order. A reaction is zero order in a particular reactant, but they do happen. In that case, I wouldn't have a curved line in the beginning. In the beginning, I wouldn't have to do anything to linearize this. It just comes out straight on down, and that's called zero order. It's rare because usually the rate of the reaction depends on concentration to some degree, but if it's to the zero order, anything to the zero is a 1, so indeed the rate is some kind of constant described by the slope of that line. Interesting. Alright, oh, here's another one. That's a good graph. Very informative. Looks like this N205 species is now I wouldn't necessarily know if it's first order or second order, because the straight up concentration decays in a curving fashion as time goes along, if I can speak today. And let's see, oh yeah, and look at the half-life. The half-life, well, I started at 0.1, half of 0.1 is 0.05, and half of 0.05 is 0.025, and half of that is somewhere in here. And so from 0 to 100, from 100 to 200, from 200 to 300, and again from 300 to 400, we see it get cut in half, cut in half, cut in half. half. And I see that indeed the half-life time stays the same across the board. So 100 seconds, 100 seconds, 100 seconds. Knowing this half-life thing, if the half-life stays constant across time, then that's another way of knowing or being aware of the fact that it's a first order decay. First order is pretty common. The mathematics, if you're comfortable at least a little bit with logarithms, or treat them as a function, a button on the calculator if you like. Yeah, where was I going with that statement? I forgot. Let's look at that one more time. And again, well, go back and look at that on the PDF for this video. Alright, so you should know that trick. It's sort of tricky, but not impossible. Let's see, especially if we compare it to a second order, but let's not go there just for this second. Here I have the natural log of this concentration, N2O5. Oh yeah, this is the same species I had earlier. Looks like they linearized the data by taking the natural logarithm, and then that slope of that line ends up being the rate constant, or the negative of the rate constant. I said, aha, since the natural logarithm of the concentration linearized the graph, looks indeed like it's first order in N2O5. Or I could also have determined that if I knew the half-life stayed constant across the board. Alright, just another one. Oops, sorry about that. Let's see. Again, the concentration versus time, almost always curvy. They took the natural logarithm of this species A, and it didn't linearize it too well. That looks sort of straight, but I can get a much better result by taking the reciprocal and versus time. So the conclusion from this particular slide is, if the natural logarithm doesn't linearize the data, but the reciprocal does linearize the data, then I know it's second order in A. Here's one. They didn't even bother to graph the straight up C4H6 concentration versus time. They just went ahead and took the natural logarithm. Seeing that's curved, they took the reciprocal of that data and regraphed again. You can use Excel, you can use any other data analysis app or graphing calculator to do it. So second order in C4H6, I would have to say. Here's one of those rare cases where versus time, the concentration straight up versus time just goes straight on down instead of curvy, and so I call this zero order. The slope is equal to the negative of the constant, and the constant is the rate, according to the rate as dictated by this species and its reactivity and the temperature. Oh, through all this, we're not even mentioning temperature, and most of you know how increasing temperature affects the rate. I've been told that a zero order, I've not tried it and measured it myself, but an example of a zero order reaction is the sublimation and subsequent redeposition of carbon dioxide dry ice. Looks like they have a burner down here, a chunk of dry ice here that sublimates from a solid to a gas and then recondenses as crystals up onto this cool test tube, and the rate of that going from here to here is zero order. We say zero order as with respect to concentration because as long as I have some dry ice down there, it should sublime like it usually does. And perhaps temperature and pressure have more to do with the rate of that sublimation than does the concentration of those particles or the number of them. Here's a very informative graph. There's the zero order, very rare, and first order and second order look very similar. Yeah, they look almost identical. And you couldn't really, obviously the first order falls faster than the second order, and that's something to try to keep in your brain if you could. Be nice if you were comparing. First order falls faster than second order, but if you have nothing else to reference it to, this looks the same as this. And it's, I swear, impossible to tell without some data and more mathematical analysis, or you could take, this curve and try to, or data points in this curve and try to fit it with some kind of regression power regression, a logarithmic or exponential or reciprocal regression. So if that's true, one reaction, reactant A, reactant B, concentration falls. Which reactant is first order? Which reactant is second order? If I told you there were one of each. Let me sneak a peek. What did I say? Oh yeah, first order falls faster than second order. So I would have to say first order in B, second order in A for this hypothetical reaction. These are the very, very informative, but I would have to say slightly lesser of importance, but interesting to think about. So here's my zero order. Here I'm graphing the rate. The rate stays constant. Looks like 0.015 for the rate here. Anything to the 0 is 1, so that little constant there would be 0.015. Gosh, this constant here would be the slope of this line. That's, let's see, the rise is 0.015 divided by 1. I'm confused. Well, anyways, but look at second order curve. If I graph the rate versus the concentration, not so linear. Interesting. And lastly, check this graph, not a graph, check this summary out. I think this is a very useful table. Don't memorize it, except for maybe, I don't know. This is this is zero order. Okay, so this line, the integrated rate law results, those are pretty important. And this is pretty good to know, and this is pretty good to know. Those are interesting. Memorization, this is good to know, this is good to know. This is kind of weird, but it's true. You'll be given most of these on our next midterm exam, and perhaps even the final as well. I can't remember what equations are given to us on the final for the course. Oh, soak that all in, guys. Thanks for watching, and I'll see you in class. Take care.